Safe at any speed. I'm Ray Myers. Welcome to Craft vs. Cruft, and I'm quite excited for this one. As you may know, 2024 is the year of formal methods on this channel, and I've been exploring ways of using formal verification to verify a refactoring process. And my favorite exercise for demonstrating this is our old friend Gilded rows, which you can find over here on Emily Bache's GitHub. You find it in a ton of languages, not oddly enough the languages that we're going to be working with today. But I've done some hasty conversion from the Lisp and Haskell versions. Now I'm going to show you the complete refactoring workflow using the Acl2 Theorem prover, which stands for a computational logic for applicative common Lisp. But very briefly, I'm going to show you where I got the inspiration for this a couple months back, and it just took me this long to figure out how to present it. So we are here in the COQ Theorem prover, and I've implemented in the sub-language Galena of that prover a Gilded rows implementation, which is purely functional, so there's no modifications. Meaning to update the item, it just returns a new copy that has been modified from the original. We have a reference copy here that we're going to call the original, the legacy code we must be consistent with. And I've just made, in this case, a very small change to it. I've got a version of it that just takes the individual fields on item instead of the entire item as an argument. So essentially a tiny little method extract has happened right here. So I'm just going to have it process these definitions. Okay, it's defined those. That's all well and fine. Process that one. But this is the special part, right? Is that we can prove that the implementations match. For all item, update item equals update item ref of item. So I'm just going to process this theorem real quick just to show you, yes, indeed, it is admitted. What if I had broken the code, right? What if instead of quality less than 50, we had done quality less than 51 here? Well, what would have happened then? Well, in fact, it can't prove it under that circumstance, right? Because we're doing formal verification here, this is in some sense stronger than unit testing, which could easily miss something like this if our test cases didn't happen to hit that situation. This will cover all possible inputs. So we're back to equivalent again, but that's not even the part that I want to show you, right? It's a realization that I had as I was working on this. So on the right, you can see what's called the proof state. So I introduced that I'm about to do this proof. It says below the line is what your goal is, and there's items that will appear above the line in our proof state. Now, the way this prover works is as you go through these steps in the proof script, it's doing transformations on the right-hand side within the proof state. So if you were just to read the proof script without seeing what it's doing as it's going through them, you wouldn't really know what's going on. But as I went about proving this equivalence and others that I was working on, I realized what was happening over here in the proof state, which is that it's doing all sorts of transformations on this source code. It's doing refactoring operations in here. In some cases, I could just, do some proof steps in order to produce a refactored simplified version and copy and paste code right out of it. And that's when I realized that automated theorem provers are refactoring tools, not just in the sense that they can help you verify a change to code, but they can actually help you perform the changes. So I got really excited and I tried to tell my friends, and I said, did you know that within the proof state of interactive proof assistance, it actually does refactoring operations? And they generally said, what the heck is a proof state? What are you talking about, Ray? And so I said, okay, back to the drawing board. I need kind of a relatable way to explain this. So I wound up working with a different prover, Acl2. Now, if you haven't used Lisp, this is going to be a little weird syntax for you as well, but bear with me. I think at least from a programmer perspective, this is going to be a little more accessible. So I'm just going to start by defining a couple of functions and verifying equivalence using Acl2, just so you can see what it looks like. So as you would in Common Lisp, which this is a relative of, I would define a function using defun. And so let's define a function called double. You might guess what this is going to do. It's going to take an argument, let's say x, and then it is going to add x to itself. Raise the font a little for you. Let's implement it again. You could probably think of another way to implement this, right? We could also multiply x by 2. Okay, will it admit that? Yes, of course it will. And clever bit is now I can verify equivalence between these two. So the way I'm going to do this is the body of the theorem will simply be equals, and then the way you would normally invoke double on x and double 2 on x. These two are equal. Now, as opposed to some theorem provers, I don't actually have to declare this variable that's unbound. Often you would say for all x, or for all x that's an int or something like that, this is true of that. It's just going to know, because I haven't bound x, that it must be just some unbound variable. So will it admit this? Yes. So let me make it wrong, right? What if it's not? It's tripling it instead. Well, then what happens? Well, it can't prove it then, right? So we've demonstrated we have a way of verifying that code is equivalent. If we make it correct again, it'll even show you what rules it applied in order to do this. And with more complicated code, we might need to give it more hints in terms of what rules it ought to use. But as it turns out, for this Gilded Rose example, just stating the theorem is enough for it to be able to go the rest of the way, which is great. So let me show you what that looks like. Again, we've got a purely functional, meaning no modifications, a variable can't be changed in place, of Gilded Rose. And our update item function here, let's admit that. Excellent, it has accepted it. And just to give you the idea of what we're going to be doing, make another copy of it and an equivalence theorem. So again, define theorem, update item equal, and then called on some name and quality and sell in is equal to update item 2 of some same name, quality, and sell in. So if these are an equivalent implementation, that should always be true. Can it prove that? Yes. Now, again, let's break it, right? So let's suppose this were just less than 51 instead of less than 50. So it'll accept the definition of it. Can we prove it equivalent? Again, no, we can't. It will not admit that. So this is one axis of what I want to see happen with advancing the state of refactoring, is greater assurance. So this is really good assurance, but we also want better automation, right? Because under this, if I wanted to make it better, I would still just be stuck rewriting the code by hand. I want it to be both faster and safer. So let's first look at some syntactic transformations we could do. Now, I'm going to use a tool called Combi, which is pretty interesting for just syntax transformations. It works on a lot of languages. It'll do pretty simple things. It's a trusty tool when you learn its scope. So let's convert this update item function to one that is specific to updating aged brie. And let's do that without actually changing the code manually at all. The idea being we could replace our original update items with the special case ones and call them in like an if-else, or a cond as it would be in Lisp, and get something a lot more maintainable. So we're going to specialize this for update brie. First of all, any time that we are comparing equal name aged brie, okay, that should be true, or in Lisp, T. All right, it's done that, and I'm just going to copy this over to the original. If we compare equal name to any other thing, now that we've already replaced all the situations where it compares it to Brie, all the rest of those should be false, or in Lisp, nil. All right, accept that one. Now, if we ever have simply not t, that should be nil. Agree? And if we ever have not nil, then that should be t. All right. Now, if we should ever have and nil and then anything at all, that ought to be nil. Good. And we've also got if nil here. So if we've ever got if nil and then some a expression and some b expression, then what should that be? It should be just the b one, right? Okay, cool. And if we've ever got if t, a, and b, then that should just be the a expression, right? I mean, even seeing, we go a step further because we're at this point setting let quality equal quality. We're letting something equal to itself. That is a waste of time. So we're going to say if we ever have let of something just being set to itself as the only let, and then some body, then we can replace that with just the body. And there's something almost like that where there's a let where the first one is vacuous and the second one we actually do want to keep. So can make another rule like that. That should actually still be a let, but one that only has BC in it, doesn't have A to itself. Excellent. The indentation's a little off, but we can always fix that with a beautifier later. So I did still end up doing something for all the steps, right? It didn't do it for me, but they were all rules that I could keep and just use later. And I never actually touched the code with my hands. So that's pretty cool. On top of that, we could always plop it into Proofpad and make sure I haven't done any mistakes by saying, you know, if name is aged Brie, in that case, update Brie is the same as item, right? So let's just do that so you can see what I'm talking about, right? Update Brie equal the name of our new theorem. So we'll just make the same theorem to compare update Brie to update item, except we will just always pass that magic name into it, and it accepts it. So that was a correct refactoring, and it was automated. At least every step of it was automated, which means we should be able to assemble them into an overall automated workflow. So let's do that. We can call Combi on the command line and do just that. I will link to my repo verified refactoring, where within the examples, Acl2, and Combi script, you're able to try this yourself if you like. But here I have cobbled together the Combi commands that would do just the transformations we just did and execute them in place, right? So this is the original that we're starting with, and then I've actually compiled this into a short Bash script that is going to do several things. It's going to take the original Lisp file and copy it into a reference file, which I have in the output directory. And then it's going to copy this wrapper we're going to use at the end, which is just comparing name to the various special values, and then in the else case, calling update normal. And it will call specialized versions for all these cases, right? And then finally, this refactored version is going to be proven equivalent to the original update item. So you can probably picture at this point what the rest of the script does, right? So it's going to set up that directory, and it's going to create using very similar method that we just did. So use that process to create a copy of update item. You're going to call update normal, and then put the output here. Make one called update brie, put the output here, and so on. So this create specialized function, copy the original file, rename the function name, and then run these steps to specialize it for the name equaling that particular thing. And it's just the steps you saw. Runs it multiple times because some of them need to happen more than once, and it's not smart enough to know when it should stop and when it should keep going. So we just run it 3 times for good measure. But so far, we've just done a bunch of fancy search and replacing on the files. We don't actually know that it's right. So we do the proof section at the end, which is going to take all of this code, including the wrapper at the end, which has an equivalence theorem, and feeds it to Acl2 so we can verify that all that was correct. So now that you understand what all's happening, let me show you it running end to end. Right? We're going to call driver.sh, the script we were just looking at. It's renaming files, it's running the Combi substitutions for each of these specialized functions, which we'll look at in just a second. All right, and then it's calling Acl2, which ultimately has validated the refactor EQ theorem, which again is that the refactored version, which is calling those specialized functions, is equivalent for all inputs to the original. And here we have the refactored version. This one's just identical to the one we created in Combi live a minute ago, and similar ones for update normal and for update for the backstage passes and update sulfurous, which doesn't have any logic at all. It just returns its input back. So that's pretty cool. I mean, we could just delete that refactored code and almost instantaneously write it all over again. If we're quick enough, we can even watch it happening. So I was pretty proud of that, honestly, but need I remind you, we are not truly using automated theorem provers as refactoring tools so far. We're just using them to confirm the validity of a refactor that we perform through other means, in this case using Combi. After I had done that, I discovered this book, which is what they call libraries in Acl2, called Kestral, which has something called Simplify-Defun, which does almost the entire thing for me. So let me show you what I fed that. Right, so first we're including this Kestral book. I've got some instructions in the repo of how to build this. It's non-trivial, but assuming you've got it all included, you can bring that in. And I've got my original Gilded rows. And then I'm calling this magical method called Simplify-Defun, which you can read all about here. It's in the APT package, which stands for Automated Program Transformations. My kind of stuff, definitely. And I'm calling it on the original update item, and I'm saying there's a new name that I want you to give the simplified version, update brie-sa, which I'm using just as an abbreviation for simplified with assumptions. And the assumptions I'm passing in here is that name is aged brie. And similarly with all the others. And the only one that's different is when I simplify update item into update normal SA, I'm going to give it just not the other ones, is going to be the assumptions. So if you knew that those things were true, then what's the simplest that with the rules that it has at its disposal that it could make that function? Then, similar to the previous example, I wrap them all up into one that checks a name equaling to each of these things and calls the appropriately specialized function. And we have our equivalence theorem, right? So this is the entire setup, and you could easily imagine even doing this much be automated, right? So now I'm going to run that one, and just got a little wrapper script called run Acl2 that I use to run it. One of the reasons I like to do that is that I can get an exit code out of it because it'll look for error in there. All right, it's come back out and it was successful. Earlier I've copied the output so you can see exactly what it did. Now it's made them all uppercase, which doesn't make any difference, but it is a little annoying. Regardless, this is almost exactly the same specialized refactored versions that I had arrived on my own cobbling together all these Combi rules. You see we've got the update brief function and a theorem created and proven automatically in which we show that the assumptions equal name, aged, breed does indeed imply the equivalence of those two. We've got our update passes copy, an equivalence theorem, update sulfurous, which does nothing, a corresponding equivalence theorem, and update normal and its equivalence theorem. And again, using all those intermediate results, we had the overarching theorem that proves the total equivalence here. So there you have it. This is approximately a 30-step refactoring workflow on Gilded rows, and we've shown how to automate it in essentially a single step and run very rapidly and formally verified. Now, you would be entirely reasonable to say, Ray, that's all well and fine if I'm writing code in the Acl2 theorem prover's language, but my legacy code is not in applicative Common Lisp. In fact, it's not in Common Lisp at all. It's in, some other thing. So what I'd love to see is for us to find a way to take some of this magic, some of this formal verification technology, and use it to apply equivalent, fast, safe refactoring in more situations in industrial legacy code. So I guess I'm going to go work on that. Thanks for watching, and as it says in the Tao Te Ching, with patience, the most tangled cord may be undone. Thank you.